Welcome to the second lecture video in our Class 21 series of lecture videos. Back to alkenes. Let's look at an MO diagram. I think we discussed this at the beginning of the semester, but just to refresh, if we have a crude molecular orbital diagram for ethylene, what we have are 4 carbon-hydrogen bonds, so we must have 4 sigma carbon-hydrogen molecular orbitals. And if we have 4 sigma carbon-hydrogen molecular orbitals, we must have 4 sigma star antibonding carbon-hydrogen molecular orbitals. We're going to put these sigma carbon-hydrogen bonding molecular orbitals low in energy because we know our carbons are sp2 hybridized, and so these molecular orbitals are made up of sp2 hybrids with 1s orbitals, which is a fairly low energy combination, versus what? Versus sigma carbon-carbon bonding molecular orbital for the single bond component, the sigma bond component of this double bond between these two carbons. So what is that bond made up of? Well, a carbon sp2 hybrid overlapping with another carbon sp2 hybrid atomic orbital. And then, of course, because we're sp2 hybridized, each carbon has a p orbital left over on it, and so those two p orbitals can be combined in phase. So if their lobes are in phase, the same phase on the same side of the plane formed by the molecule, they can form a pi bond. So we have a pi bonding carbon-carbon molecular orbital. And the other combination for those two p orbitals is one in which the lobes are out of phase on the same side of the plane formed by the molecule, in which case they cannot overlap, and this is our pi antibonding molecular orbital. Of course, if we have a sigma cc bonding molecular orbital, we must have a sigma star cc antibonding molecular orbital. In terms of the important molecular orbitals in this crude molecular orbital diagram, we're interested in the highest occupied molecular orbital, highest in what? Highest in energy. And that's the pi bond. It can act like an electron donor or a nucleophile. The other orbital we're interested in is the lowest unoccupied molecular orbital, the LUMO, and that is the pi antibonding molecular orbital. This is where a nucleophile in the larger world could add its electrons to the alkene. So, I mean, two different faces, right? What's the pi component of a double bond worth? I know this is a question that you've been waiting to have answered. And so here we have what? We have a cis-deuterium substituted version of ethylene, and here we have the trans-deuterium substituted version of ethylene. How would these interconvert? Well, you'd have to break the pi bond in order to rotate around it, so there must be some transition state at some activation energy where you could do that. Perhaps having the deuteriums on opposite sides of the double bond would be a slightly lower energy than having them on the same side. So here we go. It takes about 65 kcals per mole, or temperatures of 300 to 400 degrees C, in order to break that pi bond. So the pi bond itself, that double bond component's only worth 65 kcals per mole. That's a lot less than the carbon-carbon single bond component. If you were to totally break that double bond in a homolytic fashion, so each CH2 is acting like a carbene after you've broken that bond because you've shared the 4 electrons in those 2 bonds evenly. That would cost you 163 kcals per mole. So if we know that the double bond component is worth 65 kcals per mole, how much is that single bond component worth? Oh, about 98 kcals per mole. So that's the sigma cc bond in ethylene. It takes about 98 kcals per mole to break. let us see. Bond strength in alkenes versus alkanes. Here we've got our carbon sp2 hybrid overlapping with a hydrogen 1s. That's worth 111 kcals per mole. Here we have a carbon sp3 hybrid overlapping with a 1s. It's worth a little less, 100 kcals per mole. This kind of makes sense because an sp3 hybrid has more peak character, which would be higher in energy than an sp2 hybrid. And so we would expect this bond to be a little lower in the potential well and harder to break. We'd have to put more energy in to break it than an sp3 hybridized carbon hydrogen bond. How about the carbon bond? Here we have an sp2 hybridized carbon with an sp3 hybridized carbon. That's worth about 100 kcals per mole. Well, the sp3 carbon bond is maybe only worth about 89 kcals per mole on average. So greater bond strengths for sp2 hybridized carbons. There's more S character. We could also look at acidity. Now we have to remember that acidity is a different kind of breaking of bonds. It's heterolytic breaking of bonds because one atom ends up with both electrons as opposed to splitting the electrons in the bonds. So in terms of acidity, oh my, our alkane, our sp3 hybridized carbon, geez, that's got a pK of 50. That means the conjugate base, our carbanion that would be produced if we removed a proton, is fairly basic. How about an sp2 hybridized carbon? Well, 6 orders of magnitude more acidic. It's got a pK of 44. So it's actually easier to place a pair of electrons in an sp2 hybrid. It's lower in energy than an sp3 hybrid. That kind of makes sense. What's really remarkable are these alkynes. We know the hybridization on those carbons is sp. And so the pK for that is 25 to 28. That's, 25 orders of magnitude almost more acidic than, a normal saturated hydrocarbon proton. So, it's really quite remarkable that we can pull protons off of alkynes fairly easily, but then it's understandable because we leave those 2 electrons in an sp hybrid, which is, 50% S character, so lower energy and more stable than, say, an sp3 hybrid. So we can't really correlate these acidities to bond strength for the reasons I outlined. It's a different kind of breaking of the bond where one atom ends up with both electrons as opposed to a homolytic bond breaking event where one atom ends up with one electron and the other atom ends up with the other electron. So that pretty much does it for this video. Good luck with the question, and I'll see you in the next.